Hello everyone. Today we have an interesting topic with lots of applications. Okay, and the topic is the Bernoulli principle. You probably studied this in class. You have Bernoulli principle usually presented a flow in a tube, and there are certain assumptions are made. So you have to know assumptions, etc. And this formula is given. But unless you know how this formula is obtained, you can't answer questions kind of like what I have here. So in this figure, this may be like assume like this some kind of building, and you have water being pumped in the building, and there are various floors, and maybe these valves are closed, so there's no water coming out of here, and then sometimes water coming out of here, water coming out of here, sometimes water coming from both the pipes. And so these are the values given. I'm supposed to figure out what's the pump pressure will be over here. Pump pressure will change, you will notice once we do the problem. But before we do the problem, let's look at how Bernoulli equation comes. And there is this thing that gets cancelled. That gets cancelled because A1 V1 equals to A2 V2, conservation of the volume here, right? So this means incompressible fluid. So we have assumption is incompressible fluid. That's why if this was just a gas, it wouldn't work. It works for liquid, but doesn't work for gas. Another assumption is that there's no viscosity here. You know, it's flowing with energy being conserved. Okay, so non-viscous. So these are two main assumptions, and then you just apply work energy theorem. That just means work done by non-conservative forces, which is like a pressure difference forces, will be equal to change in energy. Is change in kinetic energy plus change in potential energy. That's what that is. So what's going on here is, if you look at over here, you might say I pushed from the P. This is a P1. This force I pushed with a V1 delta T distance. And so P1 times area, so you have a P1 times area 1, that's the force, and a distance V1 delta T is the distance it got pushed. This is the amount of work done by this. A lot of people get it wrong here, because second one is where the problem occurs when you don't remember the proof, is over here I will lose energy because I'll be pushing against pressure that's outside. You're looking at only this fluid. Fluid is in this. So fluid will be pushing against the outside pressure. This is outside. Okay, so I'll lose P2 A2 V2 delta T. So this is the distance it will travel over here. Over that distance, this system will lose energy. Now that should how much energy changed? Well, one thing to notice is, let me use this. So this much kinetic energy and potential energy which used to be here got transported over there. So this, you might say, changes loss of this and gain of that. So loss of this minus half rho 1 A1 V1 delta T. So this is the volume and this is the density. Then you have a V1 square. So that's the kinetic energy. The gain of kinetic energy is the same amount, rho 2 A2 V2 delta T times V2 square. Loss of potential energy will be rho 1 A1 V1 delta T. This is the mass G H1, and gain will be rho 2 A2 V2 delta T G H2. You will see why we need this when we come to why need to know this when we come to do this problem. Okay, so we have you can see already from here is P1. If you rearrange it, you're going to get those equations. Okay, so rather than show you, you just rearrange and get that equation. All right, how does it help over here? Well, in order to cancel this, we had to have this. So when we have a pipes being branching off, this is no longer the case. Okay, we'll have to work differently over here. So let's look at over here with just two branches. You know, a whole bunch of branches shown, but basically we are dealing with this branch and this branch. So we'll do two branches, and let's see what equation we get over here, and then we will work out the numerical values. Okay, so when we look at this situation over here, we have, let's look at what happens in time delta t. So in time delta t, over here we're going to have P1, same as before. This is the force, V1 delta t. So that's the work done by the pump. And over here, we are going to have a pressure. Actually, here's the atmospheric pressure, P2. Over here will be P3. But in this example, I'm gonna, when I open the valve, it opens to the atmosphere. So these are atmospheric pressures in this example. But let's actually do a more general example. And then I'm going to have a P3, A3, V3, delta T. So I'm going to have that. And then I'm going to have the loss of energy here, and gain here, and gain here. So it's going to be minus half rho 1 A1 V1. This is the mass, V1 square, minus rho 1 A1 V1 H1. This H1 happens to be 0, and this is H2 is 10, and this H3 is that. And then I add the energy over here, rho 2 A2 V2 V2 square plus rho 2 A2 V2 H2 plus half rho 3 A3 V3 V3 square plus rho 3 A3 V3 H3. Okay, now when we arrange it, I don't get an equation like that. So simplification here can come from knowing that now A1 V1 volume that's coming over here has to go through here and here, because if both the valves are open, as is the case here in the case C, if case A or B, only one is open. So this becomes like that. So with A1 V1, the volume has to go here or here. That's equals to A2 V2 plus A3 V3. So with this, there will be some simplification, but not much, right? So in our case here, what we have is actually this area is same as this area, and this pressure is same as this pressure. So here we have a P2 equals to P3 is P atmosphere. We have A2 equals to A3, and that's D2 is pi over 4 D2 square, and A1 is pi over 4 D1 square, but D2 is half D1, so pi over 4 times 1 over 4 D1 square. So A2 is 1/4 of A1. So A2 is A3 is 1/4 A1. See, there will be simplifications here. So if I take A1, so this equation actually becomes V2 has to be equal to V3, because A2, well, let's just keep as it is here, right? So you have a A1, so V1 equals to 1/4 A2 over A1 is 1/4 V2 plus 1/4 V3. Okay, so that's the only simplification, and there's a whole combination of this that will lead to V1, right? Just to recap, for the branching situation, we found that 4 times V1 is V2 plus V3. That's one equation we found. And another equation, if you go simplify it, and I took time to simplify it, and I'm going to write this out. So P1 minus P0, and then we have a P0 over 4 V2 plus V3, which is of course going to be V1 over V1. So this whole thing kind of cancels out, and then we have minus half rho 1 V1 square plus half rho 2 you are going to get rho 2 1 over 4 V2 over V1 V2 square, half rho 2 1/4 V2 over V1, the V3 over V1 V3 square, plus rho 2 1/4 V2 over V1 H1 plus rho 3 V3 over 4 V1 H3, this H2 and H3. Okay, now we're ready to apply this. All the rows are just a single row here, We don't have two liquids flowing different places. It's the same liquid. And the V's stay here, V1s stay here because we don't know yet. So we can apply to A. So V2 equal to 0. And so equation 1 is 4V1 equals V3 and V2 equal to 0. Just put over there then P1 minus P0 is simply minus half rho, and you can see from here V3 is 12, so V1 is 3 and V3 is 12. So this is 3 square plus V2 is 0 rho. Now V3 over 4V1, this just goes away. That just becomes 1. 12 square plus plus 0 plus rho, and that's just 1 and just H3. So this is same as this, and you can see from here I can actually compute H3 is equal to 50. So we can just compute it, and this is what we want. And so this is equal to half times rho 12 square minus 3 square plus rho times G. There's a G here. Yeah, G is missing. Times G is 50 times G, and G is 10. Okay, so this one is 5 times 10 to the power 5, almost 5 times atmosphere, and this is half times 1,144 minus 9 plus 5 times 10 to the power 5. So this 500 times 135 times 10 to the power 5. So this is equal to, I get 0.675 times 10 to the power 5 plus 5 times 10 to the power 5, and that just equal to 5.675 times 10 to the power 5 Pascal. So P1 is this plus atmospheric. Atmospheric is again to 1.013 times 10 to the power 5 Pascal. So just have to add this. So 6.6 88, right? 10 to the power 5 Pascal. So that's the pressure at the pump. Okay, so when we do B, the only difference we've done is 2 and 3 are switched. So that instead of this, we are going to get that. So for B, so for A we have this answer 6.688 times 10 to the power 5 Pascal. For B, we are going to be this is the only difference. This is going to be H2, and this is going to be 10. So this is going to be 10. So this will become 1. This 10. So this becomes 1. This becomes 1. This becomes 1. Everything else remains the same. This becomes 1, and this becomes 1. So this becomes 2. So for B, it's just 2.688 times 10 to the power 5 Pascal. But for C, we are going to, this will not be 0, these zeros will not be there, so we need to redo. Okay, so now I'm going to have 4v1 equals v2 plus v3, the entire thing. Now v3 is 6, and 4v1 is, this is 12 equals to v2 plus 6. So v2 is also 6, and v1 is 3, v3 is 6. So instead of that, I'm going to have minus either row, a half row, and then I'm going to have minus 3 square plus 1/4, the whole thing. 1/4, v2 is 6 and v1 is 3 times 6 square plus 1/4 is also 6 over 3 times 6 square. So they kind of add, and then I'm going to have these guys where one was 1 times 10 to the power 5 and one was 5 times 10 to the power 5. So only difference is over here. These guys we already calculated individually potential energies. So over here, this is 2, and so this is half. So this whole thing is half. So this whole thing is 6 square. So this is half times 1000 times minus 9 plus 36 plus 6 times 10 to the power 6, and this is 27. This is 27, and we do this 14.5. No. This 27 is, this is 13.5. So this is going to be equal to 0.135 times 10 to the power 5, making everything 10 to the power 5, plus 6 times 10 to the power 5 is 6.135 times 10 to the power 5. So P0, then add 1.013, so 841.7. So for C, I'm going to have a 7.148 times 10 to the power 5 Pascal. Okay, so we really do a whole bunch of calculation here. Some of them I got lost. The upshot is when you have branching, then you have to actually apply this very carefully, because the conservation equation is a little more complicated, and you have to work with the conservation equation as well as Bernoulli. Okay, so what I'm going to do next, this was a non-standard problem, so we're going to try to do some standard problems like a Venturi tube, and other standard problems. Just to give you a flavor of what the standard problem might look like, one of the standard problems is, and maybe you can practice it, I'm going to do it in another video, but one of the standard problem is what is called, you have a tube coming out of a tank, and so this tank has maybe area cross-section A over there, and there is a there is a valve here, and you open the valve, and then the question is, if the height is given h here, what will be the flow that's going to come out if area here is, say, area is A, so what's the speed which will come out? This is called draining the tank. And we'll do this problem. There's some subtlety to this problem. It shows up a lot in the problem, in many tests. Venturi tube is another one that variations of Venturi tube show up in tests. So we are going to do that in another problem, another video. For now, I just want to remind you, a lot of these problems I address it in this website, physicsbootcamp.org. So you can go check that out. You might want to subscribe to this channel or two also. I'm trying to post one video a day, and eventually we're going to go to electricity and magnetism and modern topics. But that's we're very systematically working through Physics Bootcamp, our website, and I'm on the dynamic liquid, and the next is next series of topics after we finish with liquids will be thermodynamics. And after thermodynamics, we have electricity and magnetism coming up. Okay, so hopefully see you around, and subscribe and maybe like this video. Thank you. Bye.